All right, we are getting super close, guys. Super close. So today we're looking at 8.3. This is volume. And so we've been doing area, and we know that the area under a curve can be represented by an integral, f of x dx, where we think about it as if we have some interval from A to B, and we've got this curve, f of x, then what we have here is essentially a height. So we get the height of sort of a sliver, if you will, times this little width, which is the dx here. That's the w. And if we get those little rectangles, enough of them, we can add those little rectangles together, and those little tiny rectangles, which get smaller and smaller and smaller, those little rectangles will eventually add up and give us that area under the curve. Okay. Well, imagine, if you will, we have now an integral from A to B, and same idea, we have, instead of rectangles, what if we had a different shape? Not just a rectangle of some sort of height, but really imagine, maybe it's like a square. Like a square that comes like up off the paper, if you will, all right? And if you get enough of these little squares that are sort of popping up off the paper, do you sort of see that? Mm-hmm. All right, it's like, imagine, if you will, a loaf of bread, okay? So here's another, we've got the base of the bread, and then again, it's popping up off of the paper, and there's another slice of bread, okay? Well, so what we've got here is we've got this bread, and it has an area. So it's got this base in our field here, and it's got the height that's also that same sort of distance to the curve. Well, that would be this, if it was f of x here, whatever that height happened to be, f of x is the height, and again, here's f of x, again, that height off of the paper. Well, what we can do is now we have this little square that we are using. Oh, maybe that's f of x squared. That gives me the area of that slice of bread, shall we say. And then if I multiply that area times the thickness of that slice of bread, again, that little dx, that little width, and if we add up all of those slices of bread, there's going to be a lot of them. If we add up all those slices of square pieces of bread, then we would get this volume. Okay, so now I have what here looks to be like an area times a width. That's going to give us volume units now when we add up all those pieces of bread. So again, I really do think that a loaf of bread is the best example here. What we're doing is we're creating areas, and then we're adding up all these little areas to get the volume of the bread, if you will. And it's this three-dimensional figure. That's sort of the shape of the curve. It's kind of interesting. And so that's what we're doing today. We are creating volumes with known cross-sections. So today, they might be cross-sections. So this is a cross-section. It's if you cut your, like a brick of cheese, those big pound blocks of cheese, You take that block of cheese and you slice it straight across, all right? And then you open it up and you look at the shape, all right? If it's mozzarella, maybe it's round, like a circle, okay? but if it's a block of cheese like cheddar, it's usually a square. Okay, that's a cross section. So when you cut it and open it, what shape are you looking at? So here we have cross sections that are squares, but they could be any shape we want. And it creates a really interesting figure. So we know that we have the formula for a square. It's all just base times height. They just happen to be the same. So we could do side squared. We've got rectangles. We could use semicircles. So again, area. These are things you do have to know. You must know these. You must know these formulas. This one they would give you if you needed the equilateral triangle. But hopefully you know those. Semicircle, pi r squared is a full circle, and then if we want a semicircle, we just have to cut that in half, so divide it by 2. And we have equilateral triangle here, which again, you don't have to memorize that one. So these are using areas and then multiplying them by this little change in the x. So that's the width of the slice. And that'll give us volume. And again, thinking about units here, area units are squared units. We multiply by more of those units, you get cubic units, which is a measure of volume. Okay. So it's kind of interesting. Let's see how that works today. Okay, so for cross sections, perpendicular to the x-axis, so these are how they normally are, really. Volume is the integral from a to b of the area of the slice times dx. And everything is in terms of x. It's a function of x. So everything has x's in it. But we can also do cross sections that are horizontal, perpendicular to the y-axis. And so these things would all be functions of y. But again, it's just area times thickness, and that'll give us volume. We want to find the volume of a solid whose base is a triangle bounded by y equals negative 2x. Oh, that's the wrong page. Sorry. I'm looking at the wrong thing. It's not going to be very helpful for me. Oh, maybe I don't write it down. I wonder what I did with it. All right. I have them worked out, but I'd like to use Gary's to check it. That's super funny. I don't think I have it. All right. Here we go. Find the volume of a solid whose base is a triangle bounded by y equals negative 2x plus 2. So here's this line right here starting at 2, and then we're going down 2 over 1. So this is our y equals negative 2x plus 2 line. X equals 0. X equals 0 is the equation for the y-axis, so right there. And y equals 0 is the equation for the x-axis. So we get this triangular region. And you can see how it's all enclosed. We've got this nice enclosed region here. And we want cross sections that are squares perpendicular to the x-axis. So what we have here is I want a cross section. What we're going to do is I want a cross section that's the shape of a square. So right here, what is this height? It looks like 1. That was incidental. What is this height? How do we figure that height out? And it changes, you know. How does it change? We plug in some x value. How do we get the y value? It's just the equation. Yeah, it's our equation. So as we move along that x-axis there, our height is determined by our function. So when we look, that height really is our y value, all right, and from our function. And then what we're going to do is we want a square shape. And so I'm going to just pop that off the page there. There we go. So that I get a square. Well, to get a square, it would be base of y and a height of y. So what's the area? Y squared. Yeah, y squared is the area. And they just all popping off the page here. They're all different sizes. It's kind of interesting. They get bigger and bigger and bigger. It's hard to draw. But we get all these little squares popping off the page. And we have, so in this case, there's our, to get the volume, we are integrating between 0 and 1 on the x-axis, and the area of our shape is just y squared, or in this case s squared, but our y is our function. So we're integrating from 0 to 1, and our y function is negative 2x plus 2, and we want to square that. So there's our area, and then we're multiplying it by the little thickness there. Whew, laggy today. All right, look at that, so laggy. My hand is gone. Now I'm putting it back. Oh, no, where'd it go? Oh, there it is. It's a little laggy today. Okay, so how do we integrate this? What is the best way to do that? Multiply it out. Yeah, that is absolutely the best way to do that. So we have negative 2x plus 2, and we're going to write it out 2 times. It's the best way. It takes a second longer, but you're not going to make any mistakes. We could do a u substitution here, but we have to compensate, and so just a little bit harder. We're going to get 4x squared minus 8x. Oh, that's a 2. I'm doing it in my head. There we go. Minus 4x minus 4, so minus 8x, and then plus 4. Is that what you guys got? Okay. So we're integrating from 0 to 1 of 4x squared minus 8x plus 4 dx. All right, so we can go ahead and integrate that. Antiderivative of 4x squared. Good. 4x cubed divided by 3. Negative 8x, antiderivative. Minus 8x squared over 2 minus 4x squared. Good. And then plus 4x. We don't need a plus c because we have our 0 and 1 to plug in. All right, so then if I plug in the 1 cubed is 1, so I'm getting 4/3. Minus 4 plus 4. Oh, that makes it easy. And then I got to plug in the 0. Oh, that's just going to be 0, 0, and 0. Okay. So we get, 4/3. Hey, that was not too bad. I like that problem. Okay. All right, set up, but do not integrate. This is a very common instruction. Set it up, but don't integrate. Comes around a lot. For volumes of solids with the same base as in example 1, so the same triangular shape is the base of our 3-dimensional volume here. But with cross-sections that are semicircles, so for semicircles perpendicular to the x-axis, so again, I've got this base. Here's my semicircle. Ooh, semicircle. And what's going to happen is it's going to be a little semicircle that pops up off the page here. So there it is. There's my little semicircle. All right. A semicircle has an area of 1/2 pi r squared, okay? That's the area of a semicircle. So right now, the base of our semicircle has how long is this little base here? I guess it's a diameter. This is the length of y, which is our negative 2x plus 2. But what's the radius? Well, so like this would be the diameter of the semicircle, right? but our formula is radius. Like I have a 1/2 I. Yeah, we got to take that 2x, negative 2x plus 2 and split it in half, if you will. Radius is, we can do a little change here. It is diameter divided by 2, okay? So when we're looking at this shape, and this is where like visualizing in your head is so important. This is a semicircle. This distance represents the diameter, so I do need to cut that into 2 pieces for the radius. And so if I were to set this up, my volume is my integral from 0 to 1. So we're starting at 0 and ending at 1 here. The area of this shape, this semicircle, is 1/2 pi. Diameter divided by 2. Our diameter is that y value, which is our function. So negative 2x plus 2 over 2 quantity squared. So really, I think thinking about those areas carefully is really, really important. You can absolutely leave it like this. You do have to be a little bit careful here. I'm going to talk about this. If I wanted to clean this up, this whole fraction is being squared. What's the denominator if I wanted to clean this up a little bit? I'm going to go 0 to 1. I've got a 1/2 and a pi. This would become negative 2x plus 2 squared. And then this is 2 being squared. It's over 4. All right, so I could clean it up a little bit this way. We could also do one more thing. All of these 1/2 and the pi and the 4, they're all just scalar multiples, so we could pull all of those out in front if we wanted to. I'm not going to do that. I could pull out this is 1/8 pi. So 1/8 pi could come out in front. But you don't have to do that, but it's things we're going to talk about because it makes life easier if you do have to do them. All right, let's look at another one here. We have rectangles of height 1/4. Ooh, interesting. So what I have now is I have this shape here. Here's my, essentially the base of my rectangle. Again, that's y. That's the height of it. But then it's only going to come up 1/4. So the height of my rectangle is just 1/4. It's this little tiny squat height coming off of the paper. So the area of the rectangle, the base is base times height. Our base is our function y, and the height is just 1/4. So we're going to integrate from 0 to 1. I'm going to put the 1/4 in front, and then my y is negative 2x plus 2. So that is my height of 1/4. My base is my y coordinate from my function. All right, so there's my area of the rectangle times the x. Really, that's it? Oh, my goodness. I missed, don't ignore, oops. Perpendicular to the y-axis. Amanda, you need to read the whole problem. Well, that was nice. We did it perpendicular to the x-axis. Oh, right, color change here. Let's actually read the direction. So perpendicular to the y-axis. Ooh, interesting. Okay, I'm going to redraw this picture a little bit here. Just so, there we go. So there's our function, 0 to 1. There's our y again. So now what we want is, now we're going this direction. We want to be perpendicular to the y-axis. Okay. If we're perpendicular to the y-axis, I'm going to have this little squat rectangle popping up off the page here, where it's got this distance from the y-axis out to our curve here, our line. What do we need to do in order to go horizontally? We we had y equals negative 2x plus 2. We need to rearrange this function because it needs to be in terms of y. Right now we have terms of x, things with x's in it, so we need to solve for y. Rearrange this. I'm going to subtract the 2, so we get y minus 2 equals negative 2x, and then divide by negative 2. So I get x equals, running out of space is really my issue here, negative 1/2 y plus 1. You good with that? All right, so now what's happening is we're integrating from 0 on the y-axis up here to 2 on the y-axis. So this is my integral from 0 to 2. And our base now has to be in terms of y. So we have negative 1/2 y plus 1. That gives me my base here, and it has a height of 1/4. So I am going to multiply by the 1/4. And now this is all in terms of y because we're going horizontally. Okay. All right, questions on that one? Reading carefully is key. Always. All right, well, we got an extra problem in there. Okay. Number 3, set up again, but do not integrate. The volume of a solid whose base is bounded by y equals negative x squared plus 2 and y equals x, and whose cross sections are squares perpendicular to the x-axis. Okay, first things first, I need a visual in my brain. What shape is the negative x squared plus 2? Parabola. What's the y-intercept? Yep. The parabola shifted up 2, so there it is there. Coming downward, downward facing parabola. And then we have the equation y equals x, which starts at 0, 0. It goes up 1 over 1. That's about where it would fall, almost exactly there. Whose base is bounded by, ooh, interesting. I'm going to continue this curve. There we go. So there is our bounded region. Is this hole between the purple and the blue curve. We have this lovely little bounded region. I need to figure out what this intersection point is. I think this is at 1, 1. If I plug in a 1, yeah, negative 1 plus 2 is 1. So this is the ordered pair 1, 1. I need to figure out the other one. So I'm going to go ahead and solve. Negative x squared plus 2 equals x. So I'm just setting these two equal to each other. And then I'm going to move everything over. So I get x squared plus x minus 2. And double bubble here. X and x. Positive 2 and a negative 1. Is that right? Yes. So I get x equals negative 2 and x equals positive 1. So there's the 1. And right here is negative 2 on the x-axis. I don't really care about the y value. I really just need the x's there. Those will give me my bounds. So I'm integrating from negative 2 to 1. Now, what are our shapes here? Whose cross sections are squares perpendicular to the x-axis. So what I need to do is I need to figure out, here's the base of my square going from top to bottom. So how long is that? How do we figure out the distance between top minus bottom? Top curve minus bottom curve. Well, the top curve is negative x squared plus 2 minus top minus the bottom. All right. So that's my base of my square, and then it's got to pop off the page. Well, how do we get a square? Base times base. It's just got to be, the whole thing has to be squared. And then times our thickness. So there is our volume of squares. Shape of squares. Top minus bottom. We got little squares popping out the page here. They all grow and change size. It's kind of cool. The graphics in Delta Math are pretty cool today, if you take a second to slide the little slide thing. Okay, questions on that one? Is that okay? All right, set up the integrals for the volumes of the solids whose base is in the circle, x squared plus y squared equals 1, and whose cross-sections are equilateral triangles perpendicular to the y-axis. Interesting. All right. Well, this is mighty interesting. If we want to be perpendicular to the y-axis, then our cross-sections are going this direction. These are horizontal, which means we need everything in terms of y. Well, all right. That means I need to get x by itself here. So I have x squared equals 1 minus y squared. So I'm solving this equation so that it's only in terms of y. And then, of course, this is not a function as it's written, so I have to take a square root. We get plus or minus the square root of 1 minus y squared. Well, what's going on here? If we want to find the volume of equilateral triangles, I have to get this distance. So how do we find this distance? Horizontally, we got to use the equation. We got to do right curve minus left curve, if you will. Right side minus left side. Well, interestingly enough, the right side of this curve is the equation x equals the positive root of 1 minus y squared. And the left side of this circle is x equals negative square root of 1 minus y squared. Okay? So to figure out the base of my equilateral triangle, to figure out this whole base, I'm going to just use b for base. The base has to be right minus left. So that'd be the square root of 1 minus y squared minus the left edge, which is, negative radical 1 minus y squared. So right side minus left side. So that's the base of our equilateral triangle. All right, well, that's the base. What's the formula for the area of an equilateral triangle? Let's turn the page. It was radical 3 over 4. Oh, instead of side, base squared. Okay. So radical 3 over 4 base squared. And our base is right there. Square root of 1 minus y squared. Minus a negative, I guess I can turn that to a plus. The radical 1 minus y squared. Oh, that's interesting. So that's just 2 of them, huh? All right, I'm going to clean it up. If I want the volume then, what are we integrating from? Oh, where's our bottom point right here? Negative 1. Up here at, and what's the top of our circle? Positive 1. So from negative 1 to 1. Our area formula is right here. Radical 3 over 4. Radical 1 minus y squared plus another radical 1 minus y squared is 2 radical 1 minus y squared. Quantity squared, and all this is in terms of y. All right. Let's see, let's look at the last one here. We want rectangles in this one. Rectangles whose heights are 3 times their bases, okay? Well, the area of a rectangle is base times height. And again, this is all perpendicular to the y-axis, so we want everything with y's. Everything should have y's in it. All right, so again, our base here, there's our base. Again, it's going to be the same thing. The base is right side minus left side. So same thing, same exact thing. I'm just going to go ahead and clean that up to be 2 radical 1 minus y squared. Are you guys okay with that? Yeah? Okay. Now it says the heights are 3 times their bases. Well, if the height is 3 times the base, what do you suppose I should put for my height then? Three times the base. Yeah, there's our base. All we have to do is take that and times it by 3. So really that would just be 6 root 1 minus y squared. Does that make sense to you? Yes? So the height is 3b, and if we had a base of 2 radical 1 minus y squared, well, 3 times 2 just gives me the 6. All right. All right, so to get the volume, we are integrating once again the low to high, so negative 1 to 1 on that y-axis. And, oh, well, let's see, I guess area, I can sort of clean that up. We're just multiplying. 2 times 6 will give me 12. Oh, interesting. And then what is, I guess this becomes 1 minus y squared. Squared? Does that clean up? Because there's 2 of them, right? Yeah. You suppose they just cancel that? You don't have to do any cleanup on the AP test. But yeah, I mean, I think that that sort of cleans up real nice and just becomes 1 minus y squared. Because the square root and the square cancel each other out, dy. Again, that 12 could go out in front, so if you wanted to clean it up more, you could. All right. So really it's just figuring out what those areas, the shapes of those areas are, and then putting an integral around it. Not too bad, right? You integrate area, you get volume. Kind of interesting. All right. You have another Delta Math. Let me know if you've got questions.